In this video, I will demonstrate how to calculate the pressure loss when it comes out from the AHU. When we want to calculate the pressure losses, you have to consider the particular duct section that will contribute to the highest pressure loss. And usually, this is at the longest duct. So what do I mean by longest duct? As you can see from this very simple schematic, A, B, F, H will be the longest duct. That means the air will have to travel the longest distance from A all the way to H, compared to A, B, C, D, or A, B, C, E, or A, B, F, G. Alright, so but although usually we calculate the longest duct, but it may not be the one with the largest pressure loss. So what do I mean? Let's say you have a straight duct from A to, maybe there's a straight duct here, all the way to, maybe let's call this P. So AB, let's say O. AB, OP may be the furthest. A to P may be the furthest, but it may not have the largest pressure loss. Let's say in between there are nothing that contribute to much pressure losses, compared to over here, maybe you have a VAV damper, maybe you have a fire damper along the way. So the one that actually contribute to the largest pressure loss is the one that you need to consider. And maybe 80% of the time it should be along the longest duct. So once you identify the duct flow stream, okay, the section that contributes to the largest pressure loss, you need to look for each and every item or duct fittings, duct components that contribute to pressure losses. And after that, you have to sum them up together. So let's look at this example. Alright, so from this example, let's say we have identified A, B, F, H to be the largest, the longest duct that has the largest pressure loss. Let's go and find out what are the things that contribute to pressure losses. The first pressure loss that we can get easily is pressure loss due to friction. So as air travel along the duct, there will be friction losses because the surface of the duct is not smooth. The further that it travels, the larger will be the pressure losses. And that is what we call pressure loss due to duct friction. Alright, so even if it's a straight duct, A to B is a straight duct, there will be losses due to duct friction. Okay, next up. So once the air comes out from the AHU, it will start to move and travel along the way until it reach junction B. At B is a split junction where the air will go straight and turn right at the same time. So at this particular junction, there will be pressure loss. Okay, so the first one that we identified will be junction loss at point B. And when it continue to move forward, it will encounter the next component that contribute to pressure loss, and that is the fire damper. So fire damper will contribute to some amount of pressure losses. And next, when it continue to move, there is this particular duct fitting, we call it the elbow. Alright, so when the air need to turn left or right, is a disturbance to the airflow. So elbow will also contribute to pressure loss. And because there's no particular alphabet, so we will just call it elbow before F. So elbow before F will be the next one. Okay, then the air will continue to travel forward until it reach another junction, another T junction over here. And this is junction F. So this is the one, junction F. And there will be another elbow before it reaches the point H. So this is elbow loss before H. And finally, the diffuser will also have some pressure loss. So diffuser loss at H. So all in all, there are around seven pressure losses that you need to calculate before you add them up together. Okay, for pressure loss due to duct friction, how do we calculate the pressure loss? So the general formula is take the friction loss value, which is in Pascal per meter, multiply by the distance traveled, the distance that the air traveled. So from point A to point H what is the total distance. So you will take 5 meter plus 6 meters plus 2 plus 2 plus 2. So if you sum this up, it's 17 meters. So 1 Pascal per meter multiplied by 17 meters will give us 17 Pascal. Because each meter that the air travel, there will be 1 Pascal of pressure loss. So 17 meters will be 17 Pascal. To calculate all the pressure losses at duct fittings and components, the most critical value that you need to retrieve will be the velocity, the airflow velocity at this different section. Alright, so as we have learned in the friction loss chart, other than the round duct diameter, you can also get the velocity from the friction loss chart. So before we can plot onto the chart, we need to know what is the airflow volume. So let's refer back to the diagram again. Okay, so the airflow volume, as you can see from the diagram, FH, FG, CD and CE are all carrying 100 liter per second of air. Alright, so these four will have the same air volume. BF will have 200 liter per second of air that will pass through it. And finally, AB is the largest main duct. The main duct will have 400 liter per second, which is the sum of all the diffuser. So we have three air volume, alright, which is 100 liter per second. This is 100 liter per second. CD and CE is also 100 liter per second. And for BF and BC is 200 liter per second. And finally, AB is 400 liter per second. So we are going to plot 3 points to get the 3 velocity. So 100 liter per second is over here, and when it intersects with 1 Pascal per meter, the intersection point is over here. Alright, so these are all the small ducts at the end. Next, we have 200 liter per second. The point is over here. This is for BF and BC. And finally, AB, the main duct, is 400 liter per second. So the point is over here. Okay. So let's read off what is the air velocity. The smallest duct section is between 3.5 and 4. So it's around 3.7 meter per second. Alright. For the 200 liter per second section, it is around 4 to 5 and it's somewhere in between. So maybe around 4.4 meter per second. And finally, AB, the main duct over here, is above 5 but below 6. So maybe around 5.2 meter per second. Okay, once we have identified the air velocity, we can maybe label it down here, 5.2, 4.4 and 3.7. Let's calculate the pressure losses at the different duct fittings. So for the junction loss at point B, to calculate the pressure loss is half K rho V square. So the general formula is half K rho V square. Alright, so let's say you know what is the K value. The K value for a junction, let's say is 1.4, and for the elbows is 0.7. So pressure loss at junction B will be half K value, which is 1.4. Air density is 1.2. Velocity. Okay, so now we have a tricky situation. Because at junction B, before it enters junction B, it is traveling at 5.2 meter per second. But after it passes through junction B, it becomes 4.4 meter per second. So which velocity should we use to calculate the pressure loss at junction B? Okay, the answer is you will always take the upstream velocity. So if it's traveling this way and you are finding the pressure loss at this particular section, always take the upstream velocity. That means the velocity before it reaches the junction. So in this case, it will be 5.2. So 5.2, you sub in here and don't forget to square it. And if you calculate this out, you will get 22.7 Pascal. So repeat the same for the rest. At junction F will be half K rho. The velocity will become 4.4 instead of 5.2 now. And square it and you will get another value. For the elbow, same thing, half K rho V square, and it depends on which part it is at. So elbow before F is over here, so obviously you will take the 4.4 meter per second velocity, and finally for elbow before H you will take 3.7 meter per second and square it. And when you do that, these are the other three pressure losses that you will get. And we have two more components. One is the fire damper, the other one is the air diffuser. For these two components, we cannot use half K rho V square. Let's say we don't know what is the K value, but we have the manufacturer chart to help us get the pressure losses. Let me refer back to the charts that we have went through before and see how to get these two values, which is 5 Pascal and 3.2 Pascal. For fire damper, we will refer to this chart. Let's say we use this particular chart. What you need is the velocity. So at the fire damper is sitting at the duct section BF. So at duct section BF, the velocity is 4.4. And you will draw a vertical line upwards until it cuts the type A damper line. Alright, so once it cuts the type A damper line, then read off what is the pressure loss from the left hand side vertical axis. So as you can see from here, it is 5 Pascal. And that is how I get the 5 Pascal for the fire damper pressure loss. Next is the air diffuser. The air diffuser will supply 100 liter per second of air. So if you look down this particular column, which is in liter per second, the one that matches it is actually 111.1. So choose the one that is slightly bigger and not smaller, because you can throttle down, you can reduce the airflow by using a VAV box, but you cannot increase the airflow if the limitation is as such. So always choose the one that is bigger. So over here we have 5 choices. 1, 2, 3, 4, 5. 5 choices. So of course the one that is at the extreme left has a smallest duct diameter. But it's not recommended to get the one that is the smallest, because one, the noise level will be high. Second, the pressure losses will be high. As you can see from here, the pressure losses, if we are going to choose the smallest round duct air diffuser, it will be 25.3 Pascal. But if we choose a slightly bigger one, let's say 250 mm diameter or even 315 mm, the pressure losses will drop by quite a fair bit. In this case, we are going to choose the fourth one, because the recommended air velocity is actually 1 to 3 meter per second. And the last one, for 355 round the diffuser diameter, we will get an air velocity of 2.9. So from here, we can see that the pressure losses is 3.2. And that is how you get the two values. So now we have all the 7 pressure losses. Right from the start, we have the 17 Pascal of pressure loss due to friction. And next we have the 4 duct fittings, which consists of the 2 junctions and 2 elbows. And finally, we also have the 2 duct components, which is the fire damper and the supply air diffuser. So all these 7 values, if you add them up together, you will get the total external pressure losses of 78 Pascal. So with that, you will have to cross-check with the manufacturer AHU selection catalog and see whether it is able to meet this particular external static pressure loss.